Welcome everyone. A very good afternoon. My name is Sumit Kumar. This is week 12 of Soil Mechanics Geotechnical Engineering coursework. This course is taken by Professor Dilip Kumar Vaid sir from IIT Kharagpur. And we are in the final week of these sessions. And this coursework is going to be summed up by today. I haven't planned any extra session in the following week, so this will be going to be last week. At the end, I will summarize the entire content for you, and I am very much hopeful that this coursework will help you in some way or the other in increasing your concepts, whether you are the college going students or maybe some working professional. This must will help you, and I am also very much confident that you are able to solve the problems, assignment problems, and the examination problem which are going to take place after the completion of this session. So with this, first of all, let me introduce me myself. That my name is Sumit Kumar. I am PhD research scholar at IIT ISM Dhanbad. And some of the important instructions before going into the lecture that in this today's series, this course again run for 2 hours as of previous all sessions, and this video is recorded by me and this will be uploaded on the YouTube for your reference. If some of you are not able to attend it in online, you can see it later at any stage without any problem. And the contents like the PDFs, documents, whatever I am showing over here will also be shared with you through the Google document link, which is already shared with you by the NPTEL team. So we have read this subject from last 11 week, and we are in the 12th week, which is the final session for this soil mechanics coursework. So oh, you must have gained some knowledge. We have started with the basic concepts. We have read the nomenclature. We have read the shear strength. We have read the retaining wall. We have read Bosniak equation, Westergaard equation, and many more points. Specifically, the main focus of this lecture, what I have taken from last 12 session, I try to solve the problem. I try to give you the problems and the solutions. Apparently, I also have provided the many questions which would be helpful for you. And from the very first class, I have suggested you that try to solve the problem. If some practical discussions are there, I try to solve you from show you from some examples, and I also suggest you to perform those in the lab. Of if not able to do so, see the demonstration at some places, whether online or offline, whatever possible. So I think that will be the best idea to understand the things. And in the last session, we have read the retaining wall. We solved the problems in the class one itself. And so today we are going to read the slope stability to a slight extent. A very brief introduction I will discuss. The theoretical concept is already covered if you have attended the third lecture, which are there on the NPTEL sites or the YouTube. So you have understood the concept. So in this class, I will some briefly discuss the things slope stability concepts and then move to the problems associated with the same. So let's see that how much we could do in this class. And at the end, I have kept some slide in which the summary of the total sum of the these 12 lecture series will be present. Right. Now, first of all, as I have said that in the previous class we have read the retaining wall. In this class, we are going to read the slope stability. And if time permits, I may also take some of the problems of the retaining wall, which I feel that could be helpful. So I could take some problem of the retaining wall as well if the time permits. Irrespective of that, I have provided the questions and solution already in the shared document, so that's not the issue with anyone. So let's see first of all what discussion we coming across. So first thing which we are discussing in this class is the slope stability. So starting with very first thing is like, what do you mean by slope stability? If you have remember, when we are discussing the shear strength, I have shown you that the failure plane I have shown, and I have showed that how the certain plane could be the weaker plane from which the failure takes place irrespective of the other plane. So over there, if you recall the things, and I try to remind you to a picture which has been shown over there, in which it is presented that the failure takes place over there. I have given the example that suppose a certain specific site have the inherent strength of shear strength of 100 kPa. So the stress apply up to the shear stress applied at that specific section of 99 kPa doesn't move it in any direction. But if the stress increase from that point by a certain limit, that it crosses its equal 100, it is on the verge of failure, or it crosses 100, that is 100.1 kPa stress is applied, then the failure takes place. So over there also I have provided the thing like the shear strength is important, and in the shear strength chapter we have read the shear strength depend on the shear strength parameter, that is the cohesion and angle of internal friction, which is one of the prominent part in the slope stability itself. Irrespective of other factor, these two factors itself are sufficient to command the problem and provide the solution whatever required, right? So first of all, now what is mentioned over here, let me read it and then elaborate briefly, and then we move forward step by step. So first of all, it is has been said that soil with the strength components. So over there, let's see what the discussion is about. Then we will discuss the things separately. So first of all, it is mentioned that the contemporary method of the investigations are based on assuming a slip surface and center about which the rotates. Okay, so if the slope is there, if you could able to see over in the slide itself, let me take the laser point so that it could be visible. So if you see over here that this is the slope, so this slope get face. So if we draw a certain arc from certain line from this point and this point, which are equal in distance, it must have some center of certain radius. So in that way, we could able to identify the critical slip surface. So earlier in the conventional study, we are assuming a slip surface and a center about which it rotates, basically the center at through which this section could rotate during the failure. This is the uh, assumed critical slip surface. And second one is the studying the equilibrium of the forces acting on the surface. And third one is the repeating the process until the wash slip surface is found. So over there we assume a certain slip surface, we do the calculation for the slip, and then move forward and backward depending upon the needs and the requirements. So in the same fashion, we are going to discuss the thing over here as well. And we identify the host slip surface which could be there. After identifying the host slip surface, the factor of safety is calculated, and we could state that this much of the factor of safety, as we have identified all the critical slip surface which could be possible at that specific site, it is become sufficient, it become necessary as well as sufficient, and that we need to identify these various software programs are also there through which we could apparently or in the some other method by providing the parameters and the slope angles and the base and crest thickness or many more things, some parameter, if you provide, the software already provide the many critical failure surface, and it identify the critical factor of safety for some specific sites. Okay, so in that fashion we perform the things. Okay. Okay, no problem. Okay, so that thing we are discussing about. So in the similar manner, if you observe, in the similar manner, if you observe over here that those point of discussion are there. So if you have explored this field, you come to know that the various advanced methods are also come in picture these days. Like we are using the strength reduction method, that is based on the finite element assumptions, in which we use iterative methods. So like Newton Raphson method or many more things. So that are also things which come across these days in calculating, in finding the slope stability of for the specific sites. Now, when the ore slip surface identify the lowest factor of safety is stated, and that is going to be the critical surface through which failure takes place in adverse condition. So on the basis of that, we have identified the critical failure surface. We have identified the property. We already have the property of the specific site through which we have calculated the safety factor. Hence, the factor of safety could be stated. Now, the two different things are also over there in this regard. In this regard, first thing is like we need to know the index property of soil or the shear strength parameter and some other property to do the analysis. Specifically, we need the cohesion angle of internal friction and the unit weight of soil in order to move ahead in calculating the safety factor for the specific site. Now, slopes are also of two types, that is the infinite slopes and finite slopes. We have the infinite slope where we use factor of safety for unsaturated condition. For unsaturated and cohesionless soil, we say factor of safety equal to 10 phi by 10 beta. While if it is a cohesive soil, we say C plus gamma z cos square beta by gamma z cos beta sin beta. So in that fashion, we would able to calculate the factor of safety. Now, depending upon the presence of water table, it sometimes become for the cohesionless soil gamma dash by gamma set into 10 phi by 10 beta, or in that way we do the calculation. So those discussion we see as we move ahead. Now, moving to the next slide, we see, okay, I could not able to move to slide. Let me see. Okay. Over here, what discussion I am saying about that various critical slip surface has been made, and afterward, by performing the calculations on the same, we conclude the thing that this is the critical failure surface, and the factor of safety passing through it give the these specific value. Okay. Now this is the another Swedish slip circle method in which we calculate the factor of safety by dividing the cohesion from the weight into distance E, that is the eccentricity from the center, and in that manner we could be able to calculate the factor of safety. Right? Now we see elaborative term for that also. Over here, if you could see, it has been mentioned that the analysis intend to give the stability of the embankment immediately after its construction. At this stage, it is assumed that the soil in the embankment has the no time to drain. And the strength parameter used in the analysis are the ones representing the untrained strength of the soil, which are found either from the UCC or the untrained triaxial test without the pore pressure measure. Now, considering the figure, the sector of soil cut off by arc AB of radius R, let W the weight of the sector and G be the position of its center of gravity as undrained condition is considered. The shear strength compounded given as Cu, and taking the moment about it will give W equal to Cu into R into theta R equal to Cu into R square into theta R, because theta equal to LR, right? So in that manner, when we calculate the final factor of safety, which I am mentioning above, that cohesion divided by W into E, that comes into picture. Over here, C into L into R is the formula, L equal to R theta. Let me write. Um, This is nothing but this is C into L. L is the slang length, and L into R. C into L into R by W into E. And this L equal to R theta. C into L is equal to R theta into R by WE. Hence, this become C into R square theta by WE. Okay. Now, another thing is also there. Let understand that if this is arc, this is R, and this is L, when this is theta, right? So if it is theta, okay, theta is like look like B. So let me rewrite this. This is theta, this is R, and this is L. So in that manner, we are going to calculate the factor of safety. Furthermore, over here, it is mentioned that the effect of tension crack, that with a slip in a cohesive soil, there will be a tension crack at the top of the slope, along which the no shear resistance can be developed. In purely cohesive soil, the depth of the crack SC is given as the formula equal to SC equal to 2C by gamma, if you remember. The similar thing we have read in the retaining wall concept as well. Now, over there we have a detailed discussion about the tension crack things. Now you see, when we talk about the slope stability, the effect of the tension crack is to shorten the arc AB to AB dash, and if the crack is to be allowed for sustained angle to reduced as shown in the figure, but the full weight W of the sector is still used in order to compensate for water pressure that may be examined if the crack fills with rain water. Right? No problem. Now, you see over here a question is mentioned. So let me solve it very quickly. If it has not been solved already, so I will solve it very quickly. If let me read first. The figure give the detail of an embankment made of the cohesive soil with phi equal to 0, C equal to 20. The unit weight of soil is 19 kilonewton per meter cube. For the trial circle shown, determine the factor of safety against sliding. The weight of the sliding sector is 346 kilonewton, acting at an eccentricity of 5 meter from the center. What would be the factor of safety if the shaded portion of the embankment were removed? In both cases, assume no tension crack develop. Okay, so this question is based on this concept only, that is Cu into R square into theta by W into E. So over here, let me explain the thing only. So W is given as 346, capital W, while cohesion in this problem is 0. Sorry, cohesion in this problem is 20, and angle of internal friction is 0, and theta is equal to 70 degree, R equal to 9. So you calculate, let me write everything, then you do the calculation by yourself. So first of all, R is 9 meter. I will write 9 only, and L is equal to R theta. So you do this like do like R is 9 into theta. Theta is like 70 and they convert it in radian. 70 into pi by 180. Okay. So convert it in radian and find the value of L. L is found, R is found. So and W is given. E is also given as eccentricity is 5 meter. Okay, so when you calculate and cohesion is 20 and phi is 0. So when you calculate C into L into R divided by W into E, everything is known. You could able to calculate the answer, right? Now move to the next thing. Next thing is like that. Next thing over here is that with the partial saturated soil, as I have mentioned earlier or as well, partial saturated soils, the undrained strength envelope is no longer parallel to the normal stress axis, and the soil has value of both cohesion and angle of internal friction. Then the total stress analysis can be adopted to cover this couch by accessing a slip circle, slip circle produce and dividing the sector into the suitable number of vertical slices. The stability of one such slice being considered in the figure as given ahead. If you could see over there here, this discussion is mentioned in which you see the failure slope surface has been presented in which the arc is drawn of angle theta and r is the radius. Now we see the certain slice from that and the effect of tension crack over again over here can be allowed for, and in this case SC become 2c by gamma. If you remember over there, the 2c by gamma, and the tension crack has been said as um, 2c by gamma over here. This equation get turned to 2c by gamma into tan 45 plus 5 by 2. Now, over here only the total stress analysis can be adopted to cover this couch by assuming a slip circle procedure and dividing the sector into the suitable number of vertical slices. The stability of one such slice being considered um, in the figure in the following slide as I have shown earlier, and at the base of the slice is at the base of the slice set of it is the weight to some scale. Draw a direction of its normal component and end by completing the triangle of the forces. The magnitude could be determined together with the magnitude of the tangential component, that is n and t. We could able to evaluate. Over here, the effect of tension crack can be taken and it could be given look like this. Now you see that by taking the moment about the center of rotation of O, the T could be found at R the summation of T. Similarly, the resistance force also content of the normal component in which the cohesion is in with the we write C into R into theta plus summation of n tan phi by summation of T, where summation of n is the summation of normal component of forces, while the summation of T is the tangential component of forces. Now, when you move ahead, you see that these correlation are look like similar to that correlation over there. We use C into R square theta by W into E. But over there, the cohesion term is only there. But when the angle of internal friction are also there, we use this correlation to calculate the factor of safety. Now, and the other point which It's important to mention over here that the center of the most critical circle can only be found by the trial and error method, with the various slip circle being analyzed and the minimum factor of safety eventually obtained. A suitable procedure is suggested in figure below. The center of each trial circle is plotted and the F value for the circle is written alongside it. After the several points have after the several point have been discussed, it has it could be said that after the several point or after considering the several critical circle sections, this has been established that it is possible to draw the continuous f values for the factor of safety value for the different slip circle, which are roughly elliptical, so that their center indices where the center of the critical circle will be. No, one point important to note over here that the value of f is more sensitive to the horizontal movement of the circle center than the vertical movement, and it could be easily understood that if the horizontal movement could be there, that would be going to be more dangerous for the stability of the slope. Hence you need to understood the thing which we are discussing over here. The horizontal component also sometimes consist of the some other stresses as well, could be the seismic at some point of time. So let's see what are the point this statement try to make. Now over here you see that we have considered the thing, and the abruptly the automatic different circle has been drawn and the factor of safety is also stated regarding the same. Now again over here some more point is mentioned that how the base failure, phase failure or the surface failure could be there in the slope stability analysis. So let's see what point are over here in this regard. So first of all, starting with the first point says that first point say that to determine a reasonable position for the center of first trial slip circle is basically not very easy in its regard. So we could do some other things in order to achieve the same. So you see that the first trial circle how we compute. So in this regard, we do study of the various type of slip that can occur is helpful. So in the case of the soil with the angle of shearing resistance that are not less than 3 degree, the critical slip circle is invariably through the toe as it is for any soil if the angle of slope angle 53 degree, and exceptions of this rule occur when there is a real or rare layer of relative stiff material at the base of the slope, which is cause the circle to be tangential to the layer. But one thing important to mention that this could be used as the thumb rule for some point of time if it is there are no possibility of considering the other thing is there. So let me read this statement again. So first is to determine a reasonable position for a center of first trial slip circle is not easy, but study of the various types of slip circle that can occur is helpful in the case of soil with the angle of shearing resistance that are not less than 3 degree. The critical slip circle invariably through the toe as it is for any soil if the angle of slope exceeds 53 degree. Hence it could be said that then exception it could be said that it is easy to find the slip surface for the first trial circle. Now you see the fall in this slide it has been mentioned that for the cohesive soil with a little angle of friction, the slip circle tends to be deeper and usually extend in front of toe. This type of circle can, of course, be tangential to a layer of stiff material below the embankment, uh, which limits the depth to which it would have been extended. Now, see over here the all three figures on there are four figure has been presented. in which earlier what we have discussed about the toe failure, and the phase failure and the base failure or the deep circle, whatever we say. So let's see one by one. First one has been presented as a toe failure, in which if you could see, over here, here the failure takes place from the toe. That's why it has been said to be toe failure. Now it has been mentioned earlier that if the angle is the slope angle is greater than 30 degree, 30 degree there, not 3 degrees. So the circle tangential is base failure. So over here you see that the failure takes place from the base. Now the deep slip failure, in which the failure takes place at this point, at the surface base, is why it is said to be deep slide circle. And the other one is the circle tangential to the deeper stiff layer. Over there, if you consider the angle, and that is the radius, when you join the 2 point, that the point of rotation for that specific slide slope, you found that it takes place from the very different angles, and it look like as shown in the figure D. Now, and some other points has been mentioned over here, that the angle, what could be the angle of slope, like 60 degree. So angle alpha and beta, what is this term? And let me see in the next slide. So these are the some points which has been shown over here, but this discussion is not mentioned over here. So some elaborative term regarding the same could not be provided at this point of time. I will see once the lecture, and if required, I will add the point considering these things. Right. Now, let's read about some techniques provided by different investigator over the period of time regarding the slope stability. So first of all, it is said that the what technique which discuss about the alpha beta has been adopted by Jumix in 1962, and over there he has used the Fellini circle. Okay, so this thing is not very much elaborative over here. So this is clear from the lecture only. So if you have seen the lecture, that's okay. If you haven't seen, please try to go ahead with that, and get the elaborative description regarding this over there only. Now, you see, when we talk about the methods, like we have the slip circle method, we have jumbo method, we have friction circle method, we have the method of slices, and many more methods are already there for the slope stability. But in talking about the previous method, that is, and it say that such a method can only be used as a means of obtaining the sensible position of the trial slip circle when the slope is triangular, or when there is just poor pressure in the soil. The conditions are not homogeneous, and the method becomes less reliable in those circumstances. Now see, over here another question has been mentioned, in which it is said to calculate the factor of safety and the slip circle as shown. So let's see what slip circle is shown over here. If it is there, we will see the thing how and in what manner the thing has been mentioned. Okay, so the figure is mentioned. Let me read the question first. The question says the embankment in the figure is made up of soil with phi, that is the angle of internal friction 20 degree, and cohesion of 200 kilonewton per meter square, 20 kilonewton per meter square, sorry. So the soil on which the embankment sit has the angle of internal friction of 5 degree, and cohesion is 75 kilonewton per meter square for both the soils. The unit weight is 9.3 kilonewton per meter cube. So determine the factor of safety of the slip circle. So over here you see the both the term is given, and R is also mentioned, but its center could not found. So this is a little bit longer solution. So I will leave it over here only for this point of time. Once I share the document, I will provide the solution for the same. Now another type of problem which could be there, which required the maybe you could use some graph paper sheets in which you need to plot these points in order to evaluate the slip point in which we consider the various slices, and we do perform the calculations based on those slices, and moving ahead we found the elaborative solution regarding the same. Over here, this is one of the example in which we shown a classic case of the embankment resting on the stiff layer, and the slip circle is tangential to the lower layer, which gives a lower factor of safety, and slip surface is tangential to the lower surface has been presented. Now when we see over here, you see that this is what we have shown earlier, these four figure, in which it has been said that first is the toe, that the lower slope will pass through toe. The second one is circle tangential to base. So what we have seen earlier is this case also, and the other one is that in which it has been showed that the deep sleep circle is presented. Right? Let me show you. Okay, so this is the deep sleep surface, and this is the second case. What I have shown just now. Now, let me explain the things like some other points, that how we calculate the factor of safety in general for the infinite slope separately before moving ahead. So let me take a blank slide and explain the things to you before moving to the new things. Okay. Okay, see. So for infinite slope, specifically for infinite slope, right? Specifically for infinite slope, factor of safety for cohesionless soil, P0, FOS is given as 10 pi by 10 beta, dry condition, right? Okay. Now the other two cases are there in which if it is the flow takes parallel to the slope angle, over there also the distance remains the same. But if the condition is submerged condition, over there it could also be written as gamma dash, coming आगे give me a minute. Okay, everyone. Over here, we will take a 5-minute break. I will start the lecture after 5 minutes. Okay, welcome back. So before going to break, we are discussing about the factor of safety calculation scenario for different cases in which we have discussed and elaborated the point regarding the factor of safety for the infinite slopes. So what I am trying to mention that the second one is gamma dash by gamma set into tan phi by tan beta, right? Okay, so over here, this is for submerged condition. Submerged. Okay, right. So these are the cases which we are discussing about. Apart from that, we could also able to calculate the factor of safety for some other cases like okay, give me a minute again, please. Okay, so what I am saying this is for the submerged condition. Now, before moving ahead, I will give one problem to you. Please solve it, and you have a 5 minute time for that, and then afterwards we will continue. Okay. So okay, solve this problem. I will elaborate this in a while. So I think you could able to solve this. This question say the factor of safety against sliding of an embankment with C equal to 20 kPa, phi equal to 25 degree, H equal to 10 meter, and gamma equal to 18 kilonewton per meter cube. And the slope angle beta is approximately, this need to be calculated. So what the definition I have shown you recently, 2 3 slide earlier, if you have used that, you could able to solve. Let's see the solution. As I have said earlier that C plus gamma z cos square beta tan phi. This I haven't written, but I have explained this, that this is one of the correlation which one could use to calculate the factor of safety for the um, we could use to calculate the factor of safety, right? So when we have known the value of cohesion as 20, and unit weight of soil for this specific soil is 18 kilonewton per meter cube, and the angle of internal friction is also mentioned here with at 30 degree. So when we have used those and calculate the factor of safety using that correlation only, the factor of safety comes out to be 1.48. Okay, so before the coming to this question, we are discussing some of the formulas and correlations. Let's move over there. Then we will come to this slide and some of the things which we are discussing in. Okay, so let me show you some other thing as well with the help of a new slide in which we discuss the thing like over here you see we have see the cohesion and phi and angle of internal friction. For that, if you have able, we need to calculate the factor of safety for the cohesive soil. Then we use the correlation or factor of safety as C plus gamma z cos square beta tan phi in normal dry condition basically by gamma z cos beta sin beta. Okay. At the same time, if we this is normal condition, dry condition, I am not writing. You understood by yourself. And the other condition is also there when there is a submerged condition. Then this correlation converted as same as gamma dash by gamma z. It get converted into C plus gamma dash z cos square beta into tan phi by gamma z cos beta sin beta. Right. So these are the two correlation which we used. Apart from that, if it is a partially submerged, for that also we have a correlation in which we multiply gamma average we use and gamma dash we use, and in that manner we calculate the things. But at this point of time, let leave that. Once the problem come in our path, we will see and solve those things. Right. Now. Now some other points are also there. I will read this very quickly because I want to move to the questions. So over here it is mentioned that the rapid determination of a factor of safety for the homogeneous regular slope. So it can be shown that for the two similar slope made up of the two different soil, the ratio of CM basically mobilized cohesion by gamma H is same for each slope, provided that the two slope have the same angle of friction. The ratio of mobilized cohesion by gamma H is known as the stability number or the Taylor stability number, and where Cm is the mobilized cohesion mobilized regard to the total stress, and this mobilized cohesion Cm is nothing but the total C divided by factor of safety. That's why it is mobilized. That the overall cohesion at that specific section could not be used, so it is reduced in order to calculate the factor of safety, where gamma is the unit weight of soil and h is the vertical height of the embankment. Now, when we move ahead, you see the Taylor prepared the two curve that relate the stability number to the angle of slope. The first is generated general case for the C5 soil, while the second one is for the soil with phi equal to 0 with a layer of steep material for a rock at depth dh below the top of the embankment. Now, when you see these correlations over here, some equations like this comes in picture, that is also similar to summation of w or summation of n into t tan phi, the correlation which we have used earlier, that this was the similar trend for that also. Now, when we see these terms over here, in which the W is the weight, and alpha and phi is the angle of internal friction, and alpha is the angle as presented in this figure at this place, right? Now, by doing the rigorous method, if we want to apply the rigorous method to calculate the factor of safety, this is the correlations. But these are just for the basic understanding. The primary problem associated with the thing which we are discussed earlier is comes into the real field application. Now let's move to the problems one by one in order to discuss the consequence or the things which come across by understanding these concepts. So first is the multiple choice question. Basically some basic understanding to advanced understanding. I have kept the multiple choice questions followed by some elaborative problem as well. Let's see and that what are the problem over here and how we could some of the understanding regarding the same. Now, first is the main cause of slope failure in a embankment is. So the high cohesion, no. If the cohesion is good, it could increase the strength. So why the that we will be going to be the cause of the main cause of slope failure now? Yeah, low cohesion could be a chance of slope failure. So that is never be going to be our answer for this case. The second option say low permeability, right? Low permeability is also not the answer, because if there is a low permeability, that doesn't mean the slope get failed. So this is also not the answer. This is not the also an answer. Excess poor water pressure. This could be a possible answer. And high shear strength. If high shear strength, Hawaii failure takes place. So option C is going to be our correct answer for this given problem, as I understood. See, it is already come over here that the excess pore water pressure is the main cause of slope failure in the embankment, and the solution say that the excess pore water pressure reduces the excessive stress within the soil, which in turn reduces the shear strength, that is tau equal to C dash plus sigma dash tan phi, where effective stress sigma dash decreases, hence the slope become more prone to failure. That is the basic thing due to which the failure takes place across the slope body. Now, the next point, next question is the factor of safety for a slope is defined as the ratio of total stress to shear stress. No, that is not the case. Second, the ratio of resulting force to driving force. That could be a option. Next one is the ratio of pore pressure to normal stress. No, not the pore pressure or normal stress. There is no clear correlation in order to calculate the factor of safety. And the final option is the ratio of cohesion to the angle of friction. So that is also not the correct option. So option B, that is the ratio of resisting force to driving force, is the correct answer to calculate the factor of safety. So it is mentioned over here, option B. Next question say, in finite slope analysis is applicable when slope height is small, slope is long, and soil properties are uniform. Soil is purely cohesive, soil is purely frictional. So, infinite slope analysis is applicable when slope height is small? No. Slope is long and soil property are uniform could be a case. Soil is purely clay. No. Soil is purely frictional. No. So option B is the correct answer for this problem. That the slope is long and the soil properties are uniform. As an infinite slope assumes the constant soil layer extending infinitely, where the failure surface is parallel to the ground surface suitable for the uniform shallow failures. Now, the next question say critical the circular failure surface assumption in slope stability analysis was first proposed by. So whether it is Taylor, whether it is Felinius, Bishop or Jambu. So as I could say from the options, the Felinius is the correct answer. That the Felinius Swedish circle method is the method which assumes the circular failure surface and divided the sliding mass into the slices, forming the basis for the modern limit equilibrium method which we use in the present time. Next is in the Swedish circle method, pore pressure is ignored. No, fully considered, partially considered, or considered through effective stress. So basically, what I have said, no, that is the correct because it has been asked that pore pressure is not the negative sense. So ignored is the correct thing. That is the original Feldman's method assumes total stress condition, does not include the pore pressure extent explicitly. Next one is okay. Next one, read the question. Okay. The next question says that the stability number NS proposed by the Taylor 1937 is defined as. So this is C by gamma H. If you remember, NS Taylor stability number is C by gamma H. Okay. So in which option it C by gamma H? H by gamma, H gamma by C, no. C by gamma H, yes. H by F, no. Tau by A, no. So option B is the correct answer for this problem. So you see C by gamma H or C by H gamma, the Taylor introduced the stability chart using the NS for the different slope angle and the friction angle, adding a quick estimation of a factor of safety. And the next question is the stability number NS is related to the factor of safety by so if we you remember Taylor stability number NS equal to C by gamma H into factor of safety. So F equal to C by gamma HNS. C by gamma H NS. So option B again is the correct answer. This is not the answer. This is not the answer. This is not the answer. C option C. Okay, I have a doubt regarding this, but as I could understood, no. C by gamma H. No, this is wrong. This is wrong. NS equal to C by gamma HF. So F equal to C by NS gamma. This is wrong. This is wrong. Okay. And this is also wrong. So what answer I have mentioned is the correct answer, that F equal to C by gamma H NS. Next question is for the purely cohesive soil, that is the phi equal to 0, the critical slope angle for the infinite slope stability is. So again, if you remember, for this case, we do C plus gamma z cos square beta tan phi gamma z cos beta sin beta equal to 1, and as phi equal to 0, so for a purely cohesive soil phi equal to 0, the critical slope angle for the infinite slope, so this come to be C plus um, C plus 0 equal to um, tan 0 0, that's why gamma z cos square beta tan phi is 0 and equal to gamma z cos sin 2 beta sin 2 beta by 2. So this is going to be sine inverse 2c by gamma z 2 beta equal to this is going to be correct answer. Sine inverse c by gamma z, right? I've did the calculation as well, and the elaborative thing is also mentioned. Right. See, and everything, but the point of discussion is already drawn over here, and it is also mentioned over here as well. Now, the next question is that the factor of safety of an infinite slope in the dry cohesionless soil, dry cohesionless C0. So that is tan phi by tan beta. If you remember, in a slide I have discussed this thing in very detail. F equal to tan phi by tan beta. So option E is the correct answer. And that is tan phi by tan beta, and try friction now soil. The stability depend on the friction, that F is greater than 1. So slope is stable when phi is greater than beta. Now next is the rapid drawdown failure occurs due to the increase in pore pressure, sudden decrease in external pore pressure, increase in the shear strength, increase in the confining pressure. So sudden decrease in the external water pressure. So option B is the correct answer. When the reservoir water level drops, and there is a sudden increase in the water pressure takes place. That's why this type of failure takes place. Okay. So option B is the correct answer. Next is the Bishop simplified method assumes non-linear failure, or method assumes non-circular failure, negligible intense interstitial shear, full pore pressure condition, or the plane failure condition. So this consider the negligible interstitial shear Option B is the correct answer. Next is the critical circle in the slope stability passes through two of the slope, mid height of the slope, crest of the slope. If you remember, this all are the cases in each correct, but the critical circle in the slope stability passes through two of the slope could also be correct. This could also be correct. This could also be correct, but this is the critical case. Critical circle it is asked at why that is going to be answer. And the next question is the effective stress parameter governs slope stability because the the option the correct answer is also already mentioned over here in which it has been said that uh, the effective stress parameter governs the slope stability because the option B is the correct answer, that is shear strength depend upon the effective stress. Next is the pore pressure ratio. RU is defined as U by sigma U by gamma H, U by gamma WH, or U by gamma H sin by beta. As I understand, the U by gamma H is going to be the correct answer. Or and because RU is the dimensionless measure representing the ratio of pore pressure to the total overburden stress at failure. Now, the next thing is the seismic stability analysis, which we haven't read, but it is mentioned that a question I have mentioned over here just for the basic understanding. It say include the static weight only, internal force due to ground acceleration, pore pressure, or the drainage force. So the internal force is due to ground acceleration only is the seismic slope stability analysis include. The next question is the most common method used in the computer-based slope stability analysis is the limit equilibrium, finite element, limit analysis, or the empirical correlations. So the most common is nothing but option C, option A, that is the limit equilibrium method which we use at the many analysis methods. Next question is when the factor of safety equal to 1, the slope is said to be stable, critically stable, unstable, or safe. So it is in the critical stable case. Option B is going to be the correct answer for this question because it is representing the driving force and the resisting force are equal. So it is at the verge of failure. Next question is asked over here that the uh, the stability of slope improves when the water table rises or the cohesion decreases, surcharge load increases, or the water table lowers. So stability never increase when the water table rises, cohesion decreases, surcharge load increases, and the water table lowers are the two other options. But so water table lower is the only option in which the stability could increase. So option A, B, C get eliminated and the option D is going to be our correct answer. Now, when we move ahead, we see next question say which of the following increases the slope stability? And our options are increasing slope angle, reducing drainage, installing horizontal drains, or removal of toe weight. So the option C is correct, that is installing the horizontal drains will result in the increase in the slope stability and drain reduce the pore pressure, increasing the effective stress and improving the slope stability. Now the next point is the circular arc method of the slices is the most suitable for the homogeneous slopes, layered soils, rock slopes, or the retaining walls. So this is more suitable for option A, that is the homogeneous slopes, because the critical slip surface assumes the uniform soil property for the layered or the non-homogeneous slope. Non-circular method are more accurate because of their consideration or the analysis process. Next is in the Jambu method, which we have just touched and move ahead. Is the equilibrium considered is the moment only, force only, both force and moment, or none? So the correct option is force only because In the Jammu method, we use the force equilibrium only. Next is the question related to the Taylor stability number, in which we have read, and that Taylor stability number NS is C by gamma H or C by gamma HFOS, depending upon what we want to calculate. The Taylor stability charts are valid for any type of soil, purely cohesive only, purely frictional only, homogeneous slope under the total stress. So Taylor stability number is valid for homogeneous all type of any type of soil, but the homogeneous slope under the total stress. Because if the characteristic is not homogeneous, this method is not applicable, because it is used for the infinite slope condition. So that become very much important or the critical, considering the specific requirement. Next is in the slope stability problem, if C dash equal to 0, the soil is cohesive, frictional or cohesionless. If C is 0, what is the point of question? It is a cohesionless. I doesn't mean that this question need to be here also, but okay, no problem. Next question is the factor of safety against sliding. Okay, this question has been already taken earlier itself, and the solution is also discussed. So let me show the solution and move ahead with. Over here we know the C and gamma z cos square beta tan phi things are there. Gamma z sin beta cos beta is also there. When we do the calculation, the solution is easily obtained. Now the next question is, the micropile in tree can improve the stability mainly by increasing the pore pressure, reducing the soil strength, providing additional shear resistance and stiffness, or reading the confining pressure. So this is the question which I have put, additional problems. So this is basically some of the research problems related to my work. So this says the providing the additional shear resistance and stiffness. Now let's move to the summary what we have read from first class to this class, very briefly, very quickly. So we have started with the origin and classification of soil. Over there we have read about the igneous, sedimentary and metamorphic rocks. We also read about the gravel, sand, silty, clay, and the nomenclature. Over there we read the Indian nomenclature system, in which we have understood the prefix for gravel, sand, silt are GSM respectively, while the organic soil is represented by O, and the well graded, poorly graded are shown by W and P. And in addition to that, the plasticity less than 35 and 35 to 50 and greater than 50 is shown with L, I, and S symbol, and how we do the nomenclature that we have read in the very first and second lectures. Following that, we have understood the plasticity chart. P line, A line, that A equal to 0.7, A line, so A equal to 0.73 into W minus 20, and value above A line, so the cohesive material, while below is the silty, and other things related to the nomenclature we have discussed very elaborately. So that's not the issue. Following that, we have understood the basic parameter, in which we have read the void ratio, porosity. We are also understood the index property of soil. We have understood the Atterberg limit. We have understood the degree of saturation. We have understood the water content, percentage air content, everything we have understood with the help of phase diagram. Afterwards, we move ahead in the subject, and we understood the basic property like the bulk, curate, weight, degree of saturation, everything. Then we move to the permeability things, where we have understood the constant head permeability test, falling head permeability test. Apart from that, we also understood how to calculate the permeability if by taking the two of the test reservoir, and for the confined and unconfined aquifers things, those things we already also discussed in the lecture series which we are going ahead. Afterwards, following that, we have understood the permeability, calculation of permeability in the vertical or a horizontal direction. We also solved some problem where we have calculated the ratio of the horizontal permeability to the vertical permeability, and many more similar things. Afterwards, we have understood before that only with the third or fourth class, we have understood the concept of the total stress, effective stress for water pressure, and how it is developed, and how we could able to calculate how the movement of water takes place from downward to upward would converse the relations. Those things we comes to know. Following that, we have calculated the things like understood the Bosniak equation, Westgard equations, to calculate the stress at certain depth and certain section below the ground level if the load is applied at a specific section. And this concept also help us in understanding the stress developing across the soil media. Following that, we have this picture related to same. Following that, we have understood the shear strength concept, in which we have understood different tests like the triaxial test, direct shear test, vein shear test, and many more things. Afterwards, we have also come across the application of these tests, that how this application could be followed, and then the Mohr circle understanding is developed, in which we have understood that the twice the angle is made in the Mohr angle, Mohr circle, what has been found in the in general scenarios. Following that, we as I have mentioned earlier, that we have understood the direct shear test, triaxial test, UCS test, ventral shear test. With the help of pictorial representation, I have repeated these things step by step, and afterwards we have solved the problem associated with the same in very descriptive manner. Following that, uh, we have developed the understanding about the settlement, compressibility, volume compressibility, or coefficient of consolidations. The compression index and decompression index are the some of the things which we have understood. We also understood the total settlement takes place for the clay soil, and how much time it will take. Those correlations we have developed and understood, and for which we have used this relation for percentage u less than 60%, that is t equal to 5.2 percentage u by 100 square, while t equal to 1.781 minus 0.9332 100 minus percentage u for the percentage you greater than 60%. Following that, we have understood the retaining wall concept, and in this class we have discussed the slope stability to extent. So with this, we have understood the things which we have think of understanding while taking on the subject. Now, in this concluding session, up to this only things are there. Afterwards, some problems I have taken from the previous year GATE examinations. Some problems are there, 4 or 5 problems are there. So please be with me for that due course of time. And afterwards, we will close this session. And in the final session, I feel that this subject is very much easy to understand to all of you, and you could able to solve the problems and assignment problems as well as the solutions uh, of the examination, which is going to help for the certifications. So let me take these some problems, specifically 5 or 6 problems are there. Following that, we will close the session for this, for today as well as for this semester as well. Afterwards, let's see if I take some other course in the next session, next semester. If you, any one of you are interested in those courses, could join. We will meet again. Okay, so first of all, let's take these problems and then some of the sessions. So this question is basically the very first concept which we have discussed today, in which it has been mentioned that for the trash slip circle shown in the figure, calculate the factor of safety. Given weight of the soil is 346 kilonewton per meter, unit weight of soil is 19 kilonewton per meter cube, cohesion is 20 kilonewton per meter. So over here you can see C into L into R, and L equal to R theta is there, and L is nothing but 9 into 70 into pi by 180 degree. So let me solve this separately, so that see, F equal to C into, if you remember this is there in the very first or second slide only. C into L by C into L into R by W into E. So everything is mentioned over here. Cohesion is given as 20, and L is R theta. So R is 9, theta is 70 into pi, because we convert it in radian, 180. L equal to R theta multiplied by R is again 9, divided by weight is nothing but it is given 346 kilonewton per meter, 346 multiplied by 5, because eccentricity is given as 5, and when you calculate this comes out to be 1.140. This is the answer. Next question is the question number 2, in which it say true or false. The answer is already here, so try to solve by yourself. Afterwards, see the answer. The next question says the problem of slope stability analysis, assuming the circular slip surface and considering equilibrium of free body as a whole body is statically determined. So this is true. So true will be the answer. Next question is a 40-degree slope excavated to a depth of 10 meter is a deep layer. And what is deep layer we have shown through a figure in this session only, of a saturated clay of unit weight 20 kilonewton per meter cube. Relevant shear strength parameter cohesion is given, phi is given, rock is at a great depth, Taylor stability number is also given 0.18 for phi equal to 0 and beta equal to 40 degree. So from here, Taylor stability number is C by gamma h Fs, and C is given, only Fs is unknown, everything is known. So we calculate the factor of safety, and that comes out to be 2. So option A is the correct answer. Next question say a deep cut of 7 meter has been made in a clay with the unit weight of 16 kilonewton per meter cube and the cohesion of 25 kilonewton per meter square. So what will be the factor of safety? Is one has a slope angle 30 degrees, slope stability number is 0.178. So again use the same correlation as equal to C by gamma HFC and calculate the factor of safety. And that factor of safety comes out to be 1.25. Next question is the option questions in which it has been asked that with respect to C phi soil in an infinite slope, identify the following two statement true or false. So the first is the stable slope angle can be greater than phi. So it is true. Yeah. And second is the factor of safety, because this is not the case now. Beta should be less than 5 or beta should be greater than 5. Beta should be greater than 5. The second is the factor of safety of the slope does not depends on the height of the slope. So this is a false statement. So the correct answer is 1 is true, 2 is false. So B is the correct answer. Next question again is similar to the very first question, in which it has been mentioned the circular slip circle of slope is shown in the figure along with the soil property. The length of the arc is 15.6 meters. So L is already given, not no need to calculate the R theta because theta is also not mentioned over here. And the area of soil is given because weight is not given. So 82 meter square. The radius of slip circle is 10.3, and the factor of safety against the slip circle failure is nearly equal to. So resisting moment is going to be C into L into R. Cohesion is given as 30. L is also mentioned as 15.6, and R is given as 10.3 divided by weight. Weight is nothing but that area is 82 multiplied by unit weight 20 kilonewton per meter. It's come 20 into 82 comes kilonewton per meter. That multiplied by 2.3, that is the eccentricity. The factor of safety comes out to be 1.28. Now the next question and the final question for the today's session as well as the entire coursework comes over here. So this question asked that an infinite slope is to be constructed in a soil. The effective stress uh, strength parameter of the soil uh, of the C dash and phi dash, C dash equal to 0, phi dash equal to 30. The saturated unit weight of slope is 20 kilonewton per meter cube. The unit weight of water is 10 kilonewton per meter cube. Assuming the seepage occurring parallel to the slope, the maximum slope angle for the factor of safety of 1.5 would be. So Fs is again mentioned. So the same relation, because saturated unit weight and assuming seepage occur parallel to the slip surface. So tan Fs equal to, so use this correlation for this. Uh, F equal to gamma dash by gamma set tan pi by tan beta, and calculate the value of pi. And when you calculate it, this comes out to be 10.89. So this is going to be your answer. That is going to be option A. Option A will be answer over here. Option D is answer, and over here option B is answer. So with this, we come to the end of the today class. So thank you everyone for joining, and I'm also thankful for the all the students who have seen this video later on the YouTube, and I am very much hopeful that this coursework will help you in the future endeavor. So thank you everyone, and all the best for your examination and all the future endeavors. So with this, I will end the today's session as well as the entire course session. Thank you everyone.